Then um,
What are all the registers, Kana, that are present in our associative memory? Just look at the diagram.
argument register, key register, ma'am. Match
One more
register.
register.
Match register,
Okay,
ma'am.
argument. Yeah. What we have in argument register?
Uh, mm,
Actually, what we have in argument register.
um,
Similarly, what is the role of key register? Yesterday, with an example, I had explained.
yes, ma'am.
Yeah. Can you recite that?
Ma'am, key register provides a mask, ma'am.
Yeah.
Um,
Exactly.
then, um, then, then, um, mm,
Your argument register will contain the word what we are going to search for,
okay, ma'am.
isn't it? What
Yes.
I'm going to search for, that particular word will be available in the argument register, and the key register will give you the mask. That is, we are not going to compare all the bits of the word. We'll be comparing only certain bits, isn't it? So all the other bits will be masked with the help of the key register. And finally, your match register will be set to 1, isn't it? When the match register will be set to 1? When your match register will be set to 1.
If all
You have
contains
any?
one,
Uh,
ma'am,
yes, Kana, correct. If all,
contains one, ma'am.
yes, that is, if all the bits of the word in the argument register matches exactly with the word what we have stored in the associative memory. So if all the bits are 1, then the match register will be 1. Yes, very good, ma'am. Very good. Thank you, ma'am. Okay. So yeah, I'll again explain you the same block diagram because it is very essential. Once you understand it, then only we can write the Boolean expression. Okay. So see, so this is the block diagram of your associative memory where we have argument register. See my argument register, the value is I'll write it here 101. This is the word what I'm going to compare. Okay. So this is the word what I need to search for. So the word is stored in the form of bits. You all know that, and I have m words in my memory, and each word contains n bits. How many bits are there? N bits. Okay, fine. Then next comes my key register. So the value of key register is what I'm setting is like triple one, followed by all zeros, followed by R zero. So key register, the purpose of key register is to mask. Actually, it is masking. See, all these bits are masked. I'll not compare these bits because here I have masked everything. So the purpose of the key register is to mask, okay, the remaining bits of the word. So we use to compare only the first three bits. Okay. We used to compare only the first three bits because why we compare only the first three bits? Why we compare only first three bits? Give me the answer for that. No one knows
Because there is
why we compare.
one
Mm.
one in the key register, ma'am. The first three bits value is
Yeah,
one.
exactly. Yes, exactly, ma'am. So, because only the first three bits of your key register carries the value 1, and that is the reason why we take only the first three bits in the argument register and compare the word with that of the associative memory. Okay, and we used to compare it. See, parallelly, I'm writing in the diagram itself so that you can easily understand. And this is my memory, okay, and my memory is divided into words, as I told you. Each word contains n words, and totally my memory is going to contain m words. Say for example, it can be 1,000 words or 10,000 words. So m is in general notation. And every word carries how many bits? Every word contains n bits. That is bit 1. Starting from bit 1, W, if a word, so first word, first word, second bit, etc. up to first word, nth bit. Okay. So this is the notation what you have to write. This is the way you need to represent the individual bits in a particular word. So it is WI1 represents the I stands for the ith word. No, it can be first word or second word, whatever it may be, but it stands for the ith word, the first bit in ith word, the second bit in ith word, similarly up to the nth bit of ith word, because the last bit is my nth bit. Okay, so this is how my cell is being organized, and every bit, see, this is very important. Every bit is stored in individual memory cell. Every bit is stored in individual memory cell, and that cell is nothing but actually it is a flip flop. It contains certain logic circuits also. It contains certain logic circuit as well. So every cell in an associative memory contains a logic circuit. So don't forget that, because we need to do some comparison, we need to do some operations. No, so it should carry some logic circuits, like it should have some AND gate or gates, whatever is needed. It should have all the logic circuits within a particular cell. Okay, every cell is a particular, it represents two or three gates. It's a combination of two or three gates. Say, for example, AND gate or gate and your inverter, that is your NOT gate. Right. And yeah, coming to the match register, and your match register, as Reshma mentioned, your match register mi will be set to 1. It will be set to 1 only if all the bits of your argument register, matches with the word in the associative memory, matches with the word. So if everything exactly matches, my argument register, see here, I'll highlight it for you. So this is the word which I'm searching for in the argument register. And see, this is my word. This is the word which I have in my memory, in my associative memory. So when I compare whether all the bits matches, no, it does not matches. Because the first three bits here we have 101, but correspondingly in the memory the word is something like 100. So the last bit differs, right? So this does not matches. So in that case, my match register will be set to 0. That is, mi will carry the value of 0. But here my argument register is 101, and the second word, if you compare the second word, the first three bits matches. Only the first three bits matches. But in that case also, my mi will be 0. When mi will turn to 1, my mi will be equal to 1 only if all the bits of your argument register matches with all the bits of that particular word. Only in that particular case, your match register will be set to 1. Okay. So then why ma'am, that I can say that word 2 matches? How we can say that word 2 matches now? Because we have a key register. According to the key register, uh, according to the key register, I'll compare only the first three bits. Okay, I'll compare only the first three bits. So for first three bits, if I compare, then I can say that both are equal. But match register will not do that. Match register has to do all the comparison. Match register has to compare with all the rest of the bits also. So if all the rest of the bits matches, then your match register will set to 1. Then only your match register will set to 1. Okay. And I think this gives a complete picture of the block diagram gives the complete picture of your associative memory. Okay, I'll wrap all these things. So you have m words and you have n bits per word, and you know what is the role of argument register, key register, and the match register. Any doubt in this block diagram? Can we move to the next one? Karna, do you have any doubt in this? Okay, ma'am. Yeah, see, this is again, yesterday itself I also, but still I want to repeat it because I want you people to understand it very clearly. See, and here, see, Kana, argument register, say for example, this is my argument register, okay? Hmm? And the argument register contains a word. How many bit word actually? It is an n bit word. It is an n bit word. So A1 stands for A1. A1 is nothing but the first bit, the first bit in the word. Similarly, second bit, third bit, fourth bit, fifth, jth bit. AJ is the jth bit in the same word, and AN is nothing but nth bit. AN is nothing but nth bit in the same word. So a single word, I told you, every bit is stored in a particular cell. That is called as your memory cell. Okay, every bit is stored in an individual cell, and that cell carries certain logic circuits within it in order to do some match operations. So here my argument register contains a single word, and my word is nothing but it is an n-bit word. So it may contain some 8-bit word or a 16-bit word. Okay, it depends upon your OS capacity. If you have a 32-bit OS, then obviously your word representation will be 32 bits. So from the first bit till the last bit, okay, you need to compare. So I'm just separating everything. So this diagram shows an individual bit cell. So A1, A2, etc. up to J, which is your jth bit, and at last you have AN, which is your nth bit. Clear. Similarly, the key register. Key register also in the same way you have to divide the key register. Same thing. Because in the key register you can mask the bits, you can unmask the bits. That is our wish. You can mask either 3 bits or 4 bits, or you can mask 8 bits. Okay, that is our wish. But still, your key register will also represent it as an individual bit. Say K1 represent the first bit, K2 second bit. Similarly, KJ means it is your jth bit. Kn means it is the nth bit of the word. Nth bit is nothing but the last bit. Nth bit represents the last bit. Okay, so this is how every individual bit has been represented. So this is your key register. So K stands for key register. A stands for argument register. And cell, and for every memory word, and 1 minute. நான் இங்க உட்காந்துக்கிறேன். E-commerce 55 ஆச்சு. Okay. Okay, Gana. And yeah, in the associative memory also, you are dividing the memory into different cells, that is different words. And I told you that we have m words now. So word 1, word 2, word 3, ith word, etc. up to m word. Because totally we have m words. So it is organized in such a way that is starting from the first word to the mth word. Okay. And for every word, and I told you that each word has n bits now. For every word we have n bits. So C11, what do the C11 represents? C11 represents that it is the first word and first bit. I'll write it here. C11, which is nothing but Ij. Okay. I is the word number, and J is the bit position. And J stands for your bit position. Okay. So if it is C11, then it is first word, first position. If it is C12, it is first word, second bit. If it is C13, it is first word, third bit. Similarly, how many bits are there in a word? We have n bits. So it is C1n. So what do it represents? It is the nth bit of the first word. Okay, it is the nth bit of the first word. So this is how you are dividing the word into n bits, and every individual bit is stored in a memory cell. Every individual bit is stored in a memory cell. Okay. Then how we are going to set this m1? That is also important. No. So your match register will also contain m words. Your match register here. Your match register will also contain m words, because how many words are there in your memory? Similarly, the equal number of words should be there in your match register also. So if in my memory, if I have m words, in my match register also I'll have m words. So that is from m1, m2, ith word in memory. Similarly, mth word. which is the last word. Because totally we have m words. Say if it is 1,000, then m 1,000 will be the last word. Okay, that is the general notation of representing the words. So, if your associative memory have m words, then your maths register will also have m words. So, what is the size of your associative memory? The same size you have to mention in the maths register also. இங்க m, இங்க n இதெல்லாம் மாத்தி மாத்தி எழுதக்கூடாது. For that only I am saying again. Okay. Okay. So this is m1, and the point here is then m1 will be equal to 1. When m1 is equal to 1, can anybody tell me when m1 can be equal to 1? By comparing the bits, which bits will be compared? Yes,
Argument register bits.
yes. You have the bits in the argument register, exactly. All the bits in the argument register will be compared with the bits in the memory. So here I'll show you the comparison. See, your bits like A1 is compared with C11. If I have A2, okay, A2 will be compared with C12. If I have A3, it will be compared with C13. And if I have AJ, is compared with CIJ. Similarly, AN is compared with C1N. Okay, so likewise, all the bits will be compared. So if you have 1, 0, 1, 0, 0, something like that, each and every individual bit will be compared with your individual cell. Only if all the cells are equal to 1, in that case, your maths register will be equal to 1. Only if all the bits are equal to 1, like your A1 should be equal to C11, A2 should be equal to C12. Similarly, your nth bit should be equal to C1n. That is the nth bit of the first word. If it is the case, then your m1 will be equal to 1. In all the other cases, your m1 will be equal to 0. Because எல்லா words, இப்போ say for example, if I'm searching for a word, say success. Success is the word which I'm looking for in my memory. Okay. So SUCCESS. So every letter has been represented using individual bits. So every bit has to be compared. அப்போதான் entire word correct match பண்ணும். So if you're comparing only the first 2 bits or the 3 bits, அதை வச்சு maths register நம்ம ஒன்னு set பண்ண முடியாது. So you need to compare all the bits in that particular word, and then only you have to set the match register is equal to 1. But what is the role of key register over here? Key register, it will do masking. Actually, if there is a word called success, and there are some other words in the memory starting with letter A, starting with letter B, because in our dictionary we used to have words in an alphabetical order, isn't it? So it is not necessary to compare with all the words whichever there in the memory. I can directly go and compare with the word starting with letter S. I can directly go and compare with the word starting with letter S, U, C. I can have a prefix. So if it is the case, I can reduce my search time. So I can mask using the key register. I can mask the remaining bits using the key register. So only if the first 3 bits are equal, then only I go for comparing the rest of the bits. Only if the first 3 bits are equal, then I go for comparing the rest of the bits. Or else I will not take any other bits into consideration. Okay, I will not take any other bits, any other words into consideration. Okay, so this is how your argument register, key register, and the match register will work in the associative memory. Okay. So this is the one cell of associative memory. I told you, no, every bit is stored in an individual cell. Here we have seen in this block diagram, we have seen the cell. And yeah, here every individual cell of your associative memory is being given. And see here. Kana, here this in this particular cell, it contains both the read and write operation. It has both read and write operation, where if I want to store any particular data like 101 followed by 4 ones and 2 zeros. If I want to write some data using the write command, I can just enter the data into the memory. With the help of the write command, I can enter the data into the memory. Similarly, for comparison, if I want to go to for comparing the bits, if I want to compare the bits between the argument register and the memory word, okay, between the argument register and the memory word, in that case, I need to read the data from the memory. Okay, I need to read the data from the memory, and that is accomplished using read operation. Okay, now you understand what is the role of read and write operation. As of now, just imagine that Write operation, again, we are not giving any address. See, the concept of associative memory is only with the help of the content only we are going to read or write whatever it is. We are not at all going to use any address. So there is no address in associative memory. So please have this hint over in your mind. There is no address in the associative memory. If you want to perform read operation or write operation, everything is done based on the content. Everything is done based on the content alone. Okay, so if I want to read the data with the help of you, I'll give the content, I'll read the data. If I want to write the data, I'll give the content. My write operation will fetch the empty location. I told you, no, my memory cell has the capability to search for an empty space in the memory. It will search for an empty space, otherwise search for it. So it will take an empty space and it will store the content in that particular place. It will store the content in that particular place. Okay. So uh, whatever the data I'm searching for, I'll be giving it the input. Inside the cell, it is stored, everything is stored in the memory cell, and the word is available in the memory as Fij. So your Fij it is nothing but the bit of the particular word which is inside the memory. Similarly, Aij, it is the word which is inside the argument register. Okay, Fij is the word inside the memory. So whenever you want to check for matching, you need to check this Aij with that of Fij. You need to check Aij with that of Fij. Only if all the values are equal, only if all the bits are equal, then only your Mi will be set to 1. Then only the ith word, the match bit in the ith word will be set to 1. Okay, in all the other cases, your Mi will be set to 0. In all the other cases, your Mi will be set to 0. Is it clear now? So this architecture, it represents one set. See, in the match logic again, in the match logic you find AJ and the KJ. Both your argument register bit and the key register bit all are given to the match logic, and the Fij is also given. Your match logic will do the comparison between these two lines and it will set the bit Mi as 1 or 0. And it will finally set the bit Mi to 1 or 0 according to the matches. If it matches, it sets to 1. If it does not match, it will set to 0. Okay, so what about read and write operation? Write operation, it is used to store the content into the memory, and the read operation, it is used to retrieve the content out of the memory. It is used to retrieve the content out of the memory. In both the operations, we are not making use of any memory address. That is the very clear point in associative memory. Without using any address, we are going to mark the content. Can I explain panela? Because you have to write this expression by yourself. You have to write this Boolean expression by yourself. Actually, here we are performing the XOR operation. Okay, here we are performing the XOR operation. Okay, so this is AJ. This is your argument register actually. This is your argument register, and this is the word which is stored in the memory. This is the word which is stored in the memory. So you are taking the value as it is, and also you are taking the complement. Both A bar, AB plus A bar B bar. AB plus A bar B bar. It is nothing but XOR, you know. It is nothing but your XOR operation. That is what we have taken here. So this Boolean expression is very important. Only then you can draw the circuit diagram, what we are going to see later. Only then you can draw the circuit diagram. Okay. So do anybody have doubt in this particular cell of your associative memory? Can I any doubt in this architecture? This associative cell eda doubt irukama? Why no one is responding? What happened? Okay. Why? Kalimuddin, are you there?
Yes, ma'am.
Can I any doubt in this associative memory cell diagram?
No, ma'am. Clear, ma'am.
Okay, thank you. Right. So we'll move on to the next one. This particular diagram shows one cell, that is a single cell architecture. So I told you, every cell contains a logic circuit. See, in this cell, how many gates are involved? See, I have 3 AND gates and 1 NOT gate. I have 3 AND gates. 1, 2, 3. 3 AND gates and 1 NOT gate. So this many logic circuits are included in one particular cell of memory. Included in one particular cell of memory. Okay. So the next one. this logic expression, that is, sorry, this Boolean expression shows that how we are going to do the match. How we are going to do the match. Okay, so you know A and F. I told you before. AJ is nothing but the bit stored in the argument register. AJ is nothing but the bit stored in the argument register. Yes, and Fij is nothing but the bit which is stored in your memory word, that is in your associative memory. The bit stored in the associative memory. Okay. Only if both the bits are 1. That is why we have performed the AND operation over here. Only if both the bits are 1, then only your xj will be set to 1. Xj will be set to 1. I told you, no, we have to write the logic for match function. Match function என்ன லாஜிக் பண்ணா எல்லா பிட்டுமே சேமா இருக்கும். எல்லா பிட்டுமே சேமா இருக்கணும்னா ஃபர்ஸ்ட் ஆர்குமெண்ட் ரெஜிஸ்டர்ல இருக்க ஒரு பிட் எடுக்கணும், மெமரி வேர்ட்ல இருக்க ஃபர்ஸ்ட் பிட் எடுக்கணும். இது ரெண்டையும் கம்பேர் பண்ணி பார்க்கணும். ரெண்டுமே ஒண்ணா இருந்தா மட்டும்தான் xi 1 செட் பண்ணணும். இதே மாதிரி ஒவ்வொரு பிட்டுக்கும் நீ செக் பண்ணணும். ஓகே, அதுக்கப்புறம் ஃபைனலா எல்லா பிட்ஸுமே ஒண்ணா இருந்தாதான் your match register will be set to 1. So in all the cases you need to perform AND operation. You know AND gate. What is the role of AND gate? Only if all the bits are 1, only if all the inputs are high, your output will be high. Okay, that is what the purpose of using AND gate. So here in the match register, definitely enna gate da namu use panniyom. We need to use AND gate in order to do the matching. In order to do the matching. Okay. So now we have taken the XOR operation. So if only if both the bits are high, your xj will be high. Otherwise, in the complement case, if both the bits are 0, there is no match, so your xj will be 0. Your xj will be 0. So எப்ப xj value வரும் கேட்டா only if both the bits are high. Only if both the bits are high. Okay, so here we are doing the xj of, that is XOR operation. And the next one, the next important condition, I don't want to confuse you much. You just understand why this particular representation is being given. And kj, what is kj kana? K stands for what? Key register. K stands for key register. A stands for argument register, isn't it? So if your kj is equal to 1, I told you that only if the key register is equal to 1, in that time only we will be doing the comparison. And if the comparison is okay, then your xj will be written. And the particular bit match ஆச்சு அப்படினா, say for example, if I have, where is that example? Yeah, see here. Here my kj, the first bit in my kj is 1. Sorry, I can't round the first bit. It is very close. Okay, the first bit in kj is 1. The first bit is 1. In that particular case, I'll go and compare this aj with the memory word. And in that case, if both are 1, then I'll return the word xj. Xj is nothing but the corresponding let bit. Okay, then I'll return xj. Only if both the bits are 1, corresponding to the key bit, that is key register bit, corresponding to the bit in the key register. So here the same thing. Here the same thing I have written. So only if the key register is 1, your xj will be written. And if the key register is 0, that is I'm masking actually. If the key register is 0, then I'll be masking and I'll simply return 1. That's all. I'll simply return 1 because the key register is 0. Because then I'm 1 and return பண்ணாது எடுத்துக்கோங்க. Yes. அதனாலதான் இங்க I have get the complement. So here I have used the complement. So இது 1 and return பண்ணா here it becomes 0. So obviously that is masked. Okay. So the very clear point is in a single note, I can say like if key register is 1, the corresponding bit will be written. If the key register is 0, then the value will be 0. That's all. Because here it is k, here it is k complement. So if it is 1, here it becomes 0. That's all. Okay, so very simple expression. So once you understand this, so similarly for every bit, you will be comparing your argument register with that of the memory word. In every bit, it will be returned in x1, x2, etc. up to xn. Because why it is n? Because for every word, it is an n-bit word. Actually, it is an n-bit word. Okay, so it is x1, x2, x3, etc. x2, xn. So if all the bits are 1, now what we have to do? I need to do the AND operation. If all the bits are 1, then my match register will be set to 1. That is, mi will be equal to 1. If all the bits are 1, then my match register will be set to 1. Is it clear? So for this only, we are going to draw the logic diagram. For this particular thing only, we are going to draw what? A logic diagram. Okay, I'll show you that. So here, look at this particular diagram. Yeah, this is the same thing. See, when the x1 is written, this is other way of writing the match logic actually. See, the first bit, x1 is written x1, x2, x3 up to xn. All the n bits are written. All the n bits are written. Only if there is a match. Only if there is a match. And otherwise, your key register is masked. This will be 0. Otherwise, this key register will return the mask value, which is 0. Mask value, which is 0. Okay. So this is collectively, it can be written like this. Collectively, your match register. What it does actually, it compares the word with out of the argument register and the word in the memory. Or it will get the complement, or it will get the complement of the key register. Either this will be one, or this will be one, or this will be one at any point of time. Okay, so once if you understand this, only for this expression, I'm going to draw the circuit. Only if you understand this expression, we can draw the circuit very easily. Okay, so why I have written pi just for consolidating? It's a product of sums. Okay, because it is a product of sums, isn't it? It's POS form. It's in POS form, and that is the reason why we have used this pi. Because in canonical form, we have discussed that also. Okay, so pi j is equal to 1 to n. Either the word in the argument register should match with the word in the memory, or there is no match, or the particular bit will be masked, or the particular bit will be masked. That's all. So this is the complete expression. And for this expression, I'll do one thing. I'll just get this expression in the second page also, so that it will be easy for you to understand the diagram. Okay, so this is the circuit diagram which is given in your book. The same diagram I have taken here. Sorry. So we'll have that expression also. Okay. So here I'll be having this m value also. Okay. So yeah, we'll have this here. Fine. So your mi, now just to make you understand the circuit, I have given the formula over here itself. Okay. So this is what in POS form we have written this, and AJ Fij. See, first one is AJ and Fij should be directly ANDed. So I have an AND gate. Yeah, this AND gate. This is an AND gate where A1, AJ means the first bit to nth bit. That is what this is general notation. So A1, A2, etc. up to AN. Similarly, key register contains K1, K2, etc. up to KN. Similarly, your memory word contains F, I1, I2, ith word first bit, ith word second bit, likewise up to nth bit. This is the organization. That's what we have seen in the typical architecture of your associative memory itself, right? So here, AJ, Fij. So you take the value of AJ and you take the value of Fij directly, and both should be ANDed. So it is given to AND gate. So it is given to AND gate. Similarly, next one enakana AJ dash Fj dash, both should be complemented. So I need an inverter. For AJ also I need an inverter, and for Fj dash I have taken directly. Here Fi1 dash they have given it directly. The complement is given directly. So I'm taking F1 dash and the AJ dash. That is A1 dash. Fi1 dash and A1 dash. That is should be ANDed because there is a multiplication over here. There is a multiplication. That is AJ dot Fij. Dot is product. Dot is product. Product is nothing but AND form. If there is a dot, you should use AND gate. Okay, if there is a dot, you should use AND gate. So that is what given here. Similarly, Kj dash. I'm not taking Kj directly. I'm taking the complement of it. So to take the complement, I need an inverter. To take the complement, we need an inverter. So what we have to do, K1, which is your K1 dash. Okay, and finally, all these things, for all these things, we should perform an OR operation. All the three should be OR. So see, your K1 dash and your Fij and your AJ dash, Fij dash. All the three should be given to an OR gate because all are plus no. So all the three should be given to an OR gate input. Okay, all the three should be given to an OR gate input. So this is how you have to draw the circuit. The same thing, see Kana, I'll repeat once again. First AJ, Fij. For the second bit, it will be A2, Fi2. Okay, that should be under. Okay, clear. And the next one is your AJ dash, Fij dash. So AJ dash in the sense I need to go for an inverter. So I'll find AJ dash over here and Fi2 dash is directly given and there is a dot operator. So I need to perform AND operation. And the next one is your KJ dash. So K2 is directly given. To get the complement, I need to use the inverter gate. So this is my K2 dash. This is my K2 dash. Finally, everything should be OR. There is a sum between all the three inputs. So all the three outputs are given to an OR gate. Outputs are given to an OR gate. That's all. So just by looking at it, you feel somewhat complex, but once you understand the Boolean expression, you can draw the circuit for yourself. So this is the match logic. This is the circuit that has been available in our machine to do the match logic inside the associative memory. And now you can understand why associative memory is so costly. Because every cell carries an individual logic circuits, and to perform the match, we need lot number of circuits, and that is the reason why it is most expensive when compared to your main memory or cache memory. Okay, but the main important thing is whenever your search time is very critical, say you have a very critical search time that is very low search time, in that case you can go for associative memory. In all the other cases, we rely upon either main memory or the cache memory. Okay, so any doubt in this circuit diagram, in this expression, in the Boolean expression? Anybody have any doubt in this?
No,
Yes
ma'am.
or no? No, thank you. Okay, then yeah, in associative memory, we used to do two operations, isn't it? One is read, another one is write. With that, we conclude this topic, and with read operation and with the write operation. So read operation, you know that Kana here we are not going to do any duplicate values. Okay, we are not going to store any duplicate words. Once the word is stored, it is already there. It will be unique. So I can't store the word two times. Say if there is a word critical, I can't store it two times. Only once the word will be there in the memory. Okay, and my associate. So that is why we are saying that it has a unique key. Unique key is nothing but like our roll number or register number. The words will also be very unique, and only then you can go for searching the words. You can match the argument field. If there is a duplication, then there is no use of doing all these searches, having the key register and all the thing. Okay, and all these things, you know, what is the read signal? I think I don't want to say much about it. And output M of I. M is nothing but your match register. When M of I is connected to the read of the same word. So your match word, when all the bits are sent, your match word will automatically will appear at the output lines. So அந்த இடத்துல again there is no need of using any extra read command. இதெல்லாம் தேவையே கிடையாது because we are not going to use any address location. No. So if there is an address, then each and every time you need to mention the read operation with the corresponding address and all those things, all the stuffs we have to do. But here everything is read or everything is written into the memory only with the help of write operation. I mean only with the help of the content. So there is no address. There is no role to address to play over here. Okay, so the read and write operation is also very easier and it is very simple. It will take only very less amount of time as well. And the write operation. And one particular extra register is also involved in the write operation. Apart from what we have like argument register, key register, and the match register. Apart from all these register, we have another important register which is called tag register. So what is the role of this tag register actually? The tag register, it is used to set the bit to 1 if that particular memory cell is occupied. See, every individual bit is written in a cell. Isn't it? I told you that is called as one cell of your associative memory. So every bit is written in that particular cell. Say C11. What it represents, C11, what it represents, Kana? It is the first bit in the first word. So this is the cell. Okay. So if this particular cell is occupied, then your tag register will be set to 1. If the cell is occupied, your bit is set to 1. If the cell contains garbage value in the sense that cell is not used, it is not occupied. In that case, your tag register will be set to 0. Okay, because since we are not using, since we are not acquiring the help of any addresses, with only with the help of the content, and the memory has to search for an empty location also. No. So how it will do the search? Only with the help of your tag register. So if your tag register is 1, it comes to know that the particular cell is occupied. If the tag register is 0, then it comes to know that particular cell is left unoccupied, or it may contain certain garbage value. So the tag register also plays a vital role in the write operation, and it is there in the organization of associative memory. Okay, so whenever you want to store the word in the memory, you have to scan the tag register first. So while scanning the tag register itself, you come to know if that particular bit is 0, then you find that, okay, this cell is empty. So I can go and store my bit in that particular cell. This is how your memory will identify the particular cell for write operation. Right? So that's all about your read and write operation of the associative memory. So, and at last, to conclude this particular topic, so for the past 2 days, I think we were discussing the same topic, associative memory. So now you have to write from the beginning. Whenever associative memory is asked in the question paper, now you simply don't draw the block diagram. You need to write from the beginning. You have to give an intro about the associative memory. Then you have to draw the block diagram. You have to explain the diagram. And for an individual cell, you need to represent this, how the memory words are stored, how the cells are compared, and you have to mention the logic circuit of a single cell. And finally, you have to do the match logic. And after doing this match logic, you have to write out the expression, and you have to match this expression with that of the circuit diagram. You need to match this expression with it of the circuit diagram. Yes, that's it. So finally, you can write about this read and write operation. Yes. So that's all about the associative memory. In the next class, we'll be moving to the next the other topic. So if you have any doubts, you can clarify now. Any doubt in this associative memory?
No, ma'am.
Can I do anybody?
No, ma'am.
No doubts, no doubts. Okay. What about others? Only a few people are replying to me. What about others? Are you listening? Yes or no? Rajesh, are you there? Rajesh, can you hear me? Rajesh is not in the meet. Sharon, are you there, Sharon? Sharon, can you hear me?
Yes, ma'am.
Yes, Kana, any doubt in this associative memory?
Illa, ma'am.
Is it clear?
Yes, ma'am.
Okay, ma'am. Okay, thank you. Okay, Kana, let me wind up the session. Afternoon, we have EVS, so please join by 2 o'clock in the EVS session. All right, EVS meet link. I'll share it with you shortly. Right? Okay, ma'am. Thank you all. Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank you,
Thank you,
ma'am.
ma'am.
Thank you.
Thank you, ma'am.
Thank you.
Thank you.
Thank you.
Thank you, ma'am.